Well, looks to be very interesting talks coming up, and without further ado, our first speaker is Josh from Department of Statistics at LSE, and he's going to be talking about wild binary segmentation. Josh.
Thank you very much, John, and I would like to start by thanking the organizers for the invitation to this very interesting conference, which combines, of course, at least two strands of research in non-parametrics. One is change point detection, the other is non-stationary time series analysis. This talk will be in the first strand. This is a change point detection talk, of course, as the title suggests. But also, I have a student working on the extension of this to time series segmentation. So it's the other side of the story. Okay, so in fact, this talk was designed for a general audience. I probably don't have to repeat some of the things. So essentially, we're interested in the problem of detecting change points in the function f here, which is piecewise constant, and we observe it with some disturbances. So in this talk, those disturbances, this noise, will be assumed to be IID Gaussian, but this is, of course, only a toy model. It can be extended to more complex settings. What's good about this model is if your method does not work in this model, then it's not going to work in those more interesting complex settings. So that's why this is still a useful thing to play with. So what we want to do is we want to estimate the number and the locations of change points in this function f here. And mainly, I'm interested in settings where you really can't tell by a naked eye what's happening. So for example, here, I have a time series of financial returns, daily returns on the S&P 500 index. You may wonder why they are so flat, why there are no outbursts of volatility. That's because I've removed volatility. So these are the standardized returns on S&P 500. And I'm interested in discovering whether there are any change points in this sequence, which is of course obscured by noise. The signal-to-noise ratio is very, very small here. I'll come back to this example. So just to give an overview of the main classes of change point detection methods, which is essentially a repeat of what other speakers have said before me. So the main, probably the first strand of research on change point detection was to formulate a criterion to be minimized. So the early attempts were to formulate some sort of a least squares or likelihood or fit to data type of criterion, penalize it to stop it from detecting too many change points, and then minimize it. So there are some early approaches here by Yao, for example. Very good paper, by the way, etc. This trend continues to this day. There are more papers coming out with various measures of goodness of fit plus penalty. There's a very nice paper that attempts to minimize the description length of the data. That's in the context of time series rather than this simple model. There are also approaches involving L1 type penalties rather than the classical AIC, BIC. They have the advantage of being sometimes computationally more rapid to compute. There are approaches involving the classical wavelet transforms, and finally there's the binary segmentation line of research. There are more approaches. I'm not sure how SMUS fits into this. From what I understood from Axel's talk, the computation involves a little bit of binary segmentation. You subdivide previous constant intervals.
It's not it's not that type of iteration. I mean, it's really different, in nature, because you have really this global optimization problem which you solve.
Yeah.
Then at the end of the day, algorithmically, it boils down
to that's what I mean.
Recursive
right.
dynamic programming argument, but that's
okay.
just the algorithm.
Okay, let's add a dot here and saying SMUS. Fine. So as you might expect, there's no perfect perfect algorithm. They all have the advantages and disadvantages. Those penalized problems are typically pretty slow to solve. So normally these days there are algorithms involving quadratic computational complexity. There are efforts to reduce this, some by people in this audience. For example, I will mention an approach by Hui Guy, and I think the author is at least on the list of attendees. I don't know if he's here, but it doesn't matter. It does matter, but I'll continue anyway. And another approach called PELT by Rebecca Killick and her co-authors, who I know are in the audience. So I'll come back to these approaches in the simulation study. There's the minimum description length is a very neat criterion to be minimized, but the minimization itself is not obvious. The original authors did it via a genetic algorithm which returns a pretty random output. But I know again that the PELT approach goes some way towards fixing this as well. Now, the L1 type penalties are provably not optimal for change point detection, so don't use them. There's a very nice book by Brodsky and Darkowski dealing with this. So for example, if someone says I use fuse lasso for change point detection, view them with suspicion. Those type of approaches often lead to spurious detections. Classical wavelets, you can forget about them in more noisy settings. They just don't do their job. And binary segmentation, I will mention a few more details very soon. So how does binary segmentation work? Binary segmentation is very simple, conceptually very simple algorithm. First of all, we start with our data, xt, and then we fit a function, a step function, with at most with exactly one change point to the data via some sort of minimization. In this case, is least squares. It can be some sort of likelihood fit or something like that. And then, so of course, so this function will be minimized at some point. We denote that the location of that minimum by b. Then we typically test it, whether this corresponds to a significant change point. If it does, then we continue the procedure on the subintervals to the left and to the right defined by b. So we do the same fitting of always a step function with one change point to the left and to the right of our previously detected change point. And then we continue in the same way until we satisfy a certain criterion, at which point we stop. So binary segmentation is fast. It's a sort of a T log T algorithm. It's simple. It's easy to code. It's tractable theoretically with some effort, and also it's easy to extend to more complex settings. But of course, as we said, there's no perfect solution. Before I go on to that, I should also say that this minimization step, this minimization of the sum of squares here, is equivalent to a certain maximization. It's very easy to show. So if I on a generic interval from S to E, if I want to minimize this sum of squares, then it's the same as maximizing this inner product with in absolute value. What is that inner product? So X is my data from S to E on a subsegment, and this function psi is what I call an unbalanced Haar vector, which is a vector. It's a contrast vector, which is constant and positive from the start of the segment to B, and then constant negative onwards up until I reached the end of the support. So constant positive, then constant negative. It sums to 0 and it sums to 1 when I square it. So it's a very simple. Then this defines it. This is unambiguously defines the form of the function. So it's a very simple contrast function, and therefore my change point candidates B are located by looking at the maxima of this inner product in absolute values. So that's just simple algebra. There's nothing too profound in that. Okay, so from binary segmentation, when can I expect good performance, and when can't I expect good performance? If we think about what binary segmentation is doing, it's fitting a one-step function to each current interval S to E. So of course, perhaps I can expect good performance if there really is at most one change point in that interval, and perhaps I can't expect good performance if there are more than one change point in that interval. That's like fitting the wrong model to the data. So indeed, it's very easy to construct examples in which things can go very wrong if I have more than one change point in my current interval S to E. So let's see one of examples like this. What's in this figure? So the thick black line is my true function f. The thin black line is my observed data. Now the blue line is that inner product in absolute value that I showed you. It's this thing here as a function of b, so as a function of candidate change point. Now this function, this blue line, should be maximized in theory at a location where I have a change point. So either at 150 or to the left to it or to the right to it. But it's very far from that. So we can see that this function is maximized somewhere at an arbitrary location, sort of around 200, maybe 180 or something like that. And that's because this problem is kind of too difficult for the first stage of binary segmentation. That's because I have this localized feature and the change point I arranged such that in such a way that those outside change point somehow work against the main one. So it's a very difficult feature to detect for this global detection procedure resulting in this blue line. Yeah? What I really want to do is I want to get closer to this feature in order to be able to detect it. Now, how do I do it? So if I happen to start right here at 100, if I end my inner product at 200, so my S here would be 100 and E is 200, then I produce a similar inner product plotted here in the red color. Then I can see in this case the main change point is detected very nicely, so this inner product is maximized right where it should be at the main change point here. So I would like to be able to do this, but of course I don't know where to start and where to end. That's the whole thing. So now what do? We propose a method whereby I draw a selection of intervals, a selection of sub-intervals starting somewhere, ending somewhere. I draw them randomly, and I produce this Q-sum fit on each of them, on each of my randomly drawn intervals. So I draw intervals, denote them here by S star to E star. I produce those Q-sums, and then I choose the largest Q-sum, the largest value over all those Q-sums drawn. So let's have it again. So my change point candidate now is the maximum argument over not only my B, but over all the drawn intervals, S star, E star. So let's just illustrate it so that make sure everyone understands. If these are this is the domain of my data, 1 to t, I don't just fit the Q-sum starting at 1 and ending at t, but I draw a selection of intervals, and on each of them I fit my Q-sum, and then I choose as my first change point candidate, I choose the Q-sum, I choose the maximum location over all the Q-sums here. Okay, so once I've done that, then I proceed as before. This is my first change point candidate, and then I split my data to where that change point is, and then I do the same thing to the left and to the right. Okay, so what's the go on. So the lengths are selected randomly as well. I randomly select the start and the end of the interval. So I have I'm competing between very short intervals and very long intervals. But things are standardized in such a way that this doesn't matter. So it doesn't work against me in any way, and it saves me from having to choose the length of the interval. So this is parameter free. This step. Now, okay. So I can't. I can't check all the intervals, of course, because checking all the intervals would kill the computational complexity. So I have to. So this is a complexity reduction step. Now, so if the main idea of this is that if the number of draws is large enough, then I'll be able to guarantee for myself some good intervals which either contain only one change point or are very close to this situation, such as here. Okay, so if I draw a sufficiently large number of intervals, then I'll be able to guarantee good behavior for myself. Now, the nice thing is that this number of intervals I need to draw is not that large. Turns out not to be so large. I'll talk about it a bit later. Okay. So there was another thing. Right, okay, there's another thing I want to mention later. Now, so when to stop? Well, I have two criteria for stopping. One is based on thresholding. So as I essentially stop on a given interval when my maximum of all drawn intervals is less than a certain threshold. And the other is based on an information criterion where I have something very close to the Schwarz information criterion. Pronouncing this acronym directly corresponds a bit to what I felt, to how I felt of this paper after completing my major revision of it. You can pronounce it for yourselves, and then you'll see. Okay, so the way the information criterion works is by well, essentially finding the number of change points that minimize this this criterion here, which is very close to the Schwarz or Bayesian information criterion. Now, the nice thing about it is that it does improve on binary segmentation in a pretty significant way. So, first of all, there's a general assumption here which specifies the sort of the model, our universe, if you like. We have Gaussian independent innovations, and then F is bounded, and the magnitudes of the change points are also bounded from below, so no problems. This is the general assumption that we'll be using. Now, there are two different assumptions, one for standard binary segmentation and the other for this new algorithm, which I call the wild binary segmentation. The assumption for binary segmentation both concern the distance, minimum permitted distance between the change points. So for binary segmentation, the minimum permitted distance is delta t, where delta t is a certain fractional power of my sample size, so at least 3/4, actually a little bit over 3/4. Now, the analogous assumption for wild binary segmentation for the new algorithm is that the minimum spacing is logarithmic in t. So I can I can perform this algorithm for shorter spacings, and I still get consistent results. So in terms of the theory, this is of course a long theorem, but let's try to look at it carefully. So this theorem concerns binary segmentation, not wild binary segmentation, not the modification, by the standard algorithm. How does it work? Under assumptions 1 and 2, I have my true number of change points in the true locations. N doesn't have to be bounded. N can increase with the sample size. And I have estimators eta, so eta 1 to eta n are my true change points. Eta 1 hat to eta n hat are the change point estimates. Now, I use the thresholding stopping criterion, where the threshold, my threshold is, again, a fractional power of my sample size. And then I get this result here, which says that I can obtain consistent estimation of the number of change points and consistent estimation of the locations of change points, where my the distance I'm getting is this thing here. So lambda 2 is logarithmic. It's a logarithmic term which is probably inevitable in this context. And then the rest of it is t squared, where t is the sample size, divided by delta t squared. Remember, delta t is the minimum spacing. So going back to the assumption, if the minimum spacing is also linear, is also of order t, so if we are really in this locally stationary setting where we have infill asymptotics, then my distance is optimal up to the logarithmic term. Then I'm only paying the logarithmic term here. These two cancel out. However, if delta becomes smaller, so if I have a more challenging situation, then this distance becomes larger here. So this shows that binary segmentation is not optimal in the setting where the number of change points increase with the sample size and they approach each other. Okay, so that's for the binary segmentation. For wild binary segmentation, the result is better. So we provably get an improvement over binary segmentation. I also get consistency in terms of the number of change points. And then in terms of the location, I always get only log t here, irrespective of the distance between the minimum spacing between change points. So I've gained a lot here. And also the threshold, I can use a lower threshold. Firstly, there's a wider range of thresholds I can use. And secondly, logarithmic thresholds also work for wild binary segmentation, unlike binary segmentation. However, of course, I have to draw my intervals. So there's an extra condition here where my this condition essentially specifies how many intervals I need to draw. So how many intervals do I need to draw? Well, I need to draw at least m intervals, where m is, again, there's this term t squared over delta t squared, where delta t is the spacing. So if the spacing is of order t, then I only need to draw a logarithmic number of intervals in t. However, if delta is smaller, then of course this increases the required number of intervals I need to draw. Unsurprisingly, there's nothing surprising here. I need to draw more intervals if I have smaller spacings. So that's all fine. Oh, okay. I was looking for this actually. I want to say this because it's very important, I think. What happens here is this describes a very crucial algorithmic feature of the algorithm. So what happens here? I start my my algorithm, and suppose I draw 3 intervals: this one, and this one. Okay. Now they all correspond to their own Q-sums. Maybe there's another one here. Of course, some of them will overlap, intersect, etc. They are not disjoint by any means. So what happens in the algorithm? Of course, I choose this one here as my candidate change point. Now, suppose this change point is considered to be significant by my stopping criteria. Then what do I need to do? I need to then reproduce the whole thing to the left and to the right. But of course, I don't need to do that, because I've previously already drawn intervals to the left and to the right. I don't need to remove them and draw again, because I've already drawn them. So the only thing I need to do is I need to remove the intervals that already straddle my previously detected change points. So this interval here will go before the next stage. Yeah, because I only need to do it to the left and to the right and not in the middle. Yeah, so this interval will go, but this will stay, and this one will stay as well. So this suggests a very nice sort of algorithmic structure of the whole thing. So I draw all those intervals, I choose the large one, then I sort them, and then I remove those that overlap with my previous change points, but I keep the other ones, and then I continue in this way. So it's a very nice computational feature of the algorithm, I feel. Okay, let me move on. Now, of course, I need to choose the number of intervals. Okay, another interesting thing is that now, if you're familiar with things like GPU programming, if you can parallelize your algorithm, then of course, wild binary segmentation can be faster than standard binary segmentation. And why is this? Because I can send all the intervals separately to my different processors and then gather them back. In binary segmentation, I have to wait for my parents to compute before I compute. In the wild binary segmentation, there's no waiting. I can do everything independently. The only hierarchical element is this sorting and removing of some of the intervals, which is very quick. Yeah. So paradoxically and counterintuitively, this is faster than, of course, in a parallel environment, it's faster than the classical binary segmentation. So how to choose M? Well, the more the better. My student, who I will mention later, has a very nice implementation, which is very fast. Most of it is in C. So we do things like choosing 10,000 intervals for data sets of length of a few thousand, and this is a fraction of a second, so it's very, very fast. Now, how to choose the threshold? Well, we start with since logarithmic thresholds are allowed, then we start with a universal threshold which people know from wavelet denoising, and then we modify it by this constant. So these constants are chosen based on practical experience with the procedure. This constant is good or slightly overestimates the number of change points. This one is good or slightly underestimates. We still actually. I mean, I'm confident that these constants are somehow good, not bad. But this is something also to work on a little bit in the future, a bit more. And the Schwarz information criterion is pretty much constant free. If alpha was 1, this would be the Schwarz information criterion. We use a slightly larger alpha, and that's because we cannot prove that alpha equal to 1 is actually valid. But any larger alpha is. Okay, so now on to probably maybe even one of the more interesting parts of my talk. So I've, partly at the request of the referees, I've actually wanted to do a very thorough simulation study. So what I did was I went through the entire CRAN and I looked for all the packages containing words such as change or break or jump or segment. And I've long listed probably about 10 to 15 packages that do change point detection or claim to do change point, or do some version of change point detection. Then I had to unfortunately leave some of them behind because it was either not clear how to use them, or they were very slow, or they were not really suitable for this setup, or they didn't return point estimates of change points, etc. There was a lot of stuff out there which is most likely not what you're looking for. And then I was trying to also build a set of test functions to really try and see what's going on. And the first of those test functions is the block signal, which is, of course, what many of you will have seen before. Now, we're interested mainly in relatively low signal-to-noise ratio. So that's the kind of data that your procedure will see. For some of you, it will be obvious how many change points there are. For some of you may not, but that's what we did. Now, this test function is actually from Axel's SMUSE paper. He didn't show it today, I don't think, but that's one of the test function where they tested SMUSE. So I'm using it with the higher. They use it with 2 levels of variance. I'm using it with a higher level of variance here. So again, that's a representative signal. This signal I came up with it. Probably not the best example, but I wanted to have a mix of smaller change points with longer segments and vice versa. So there we are, and that's what the algorithm will get. That's what I call a teeth signal. The interesting thing is there's a change point every 10th observation, so pretty frequent, and a stirs analog of that. Okay, so what did I shortlist for competition? There's a change point package authored by Rebecca Killick and her co-authors, where they have this PELT method again. I'm not going to. I think Paul will explain it perhaps tomorrow or the day after. Then there's a method from Bai and Perron, which is implemented in the struct change package. Again, I don't even have time to go through these methods, what they do. QMSeg is a method more from the bioinformatics side by these 2 authors. And then there's a method with a very crazy name, Segmenter 3 is back. Really, check out S3IB. Okay, so for the why didn't I include SMUSE? I think I didn't include it because I realized it wasn't on CRAN. So, but I will mention SMUSE when I mention the second signal. So for blocks, what happens? Oh, and I should mention the exact commands I used are in my paper, so you can go back and see. I used all the methods with default settings. I didn't do any optimization. So what happens? So what does the table show? This table shows the number of times that the distance between my estimated number of change points and my true number of change points, and the mean square error of the resulting function estimation. So 0 is good, and anything to the left or to the right is not good. PELT. I noticed that PELT, which is, of course, I mean, they all very, very good procedures, all these. PELT actually for low signal to noise ratios, PELT tends to overestimate the number of change points. I'm not sure how fixable it is, but this is what happens, and I think it's because, again, Paul will know more. Maybe it does. Maybe it often wants to detect change points to be fast. I don't know. The authors will of course know better. By and Perron, what happens here? What happens here is that they have a hard-coded bound for the shortest segment, and this bound for the shortest segments actually hurts them here. I tried changing it, but then it made it so slow that it wasn't impossible to work with it. So it is a very slow procedure. QMSeg is it's not excellent, but I don't think it ever kind of falls apart. We will see. And then segmenter 3 is back. Is most of the time is a good stuff. So it's if you're writing a paper on change points, then you may want to include this one in your comparisons. So how does wideband segmentation do for blocks? Well, it does almost as good. So that's okay. So again, we have these two constants. One is 1, the other is 1.3, and as we can see, it's okay here. It's a little bit better here. This is kind of, well, it's in competition with the segmenter 3's back with the Schwarz information criterion. And in binary segmentation, it doesn't do too badly here. So yeah, it's still sort of in competition, I would say. Now, for the second signal from the Smuse paper, I should also recall the results from the Smuse paper. So in the table from Axel's paper, they had two versions of the procedure. One with two. So I should mention that Smuse is not an automatic procedure. You have to specify your alpha, whereas this is, for example, fully automatic here. You don't need to do anything. So in one of the versions, one alpha parameter, they had the result of 62 in this column, and for the other parameter value, they had the result of 80 in this column. So this would have placed Smuse behind this one, but ahead of all the other ones, ahead of all the non-bold ones. So here we're beginning to sort of do really well, actually, getting into very respectable performance, slightly ahead of the segmenter 3's back. Then for the mixed signal, something even more interesting happens. This signal turns out to be very, very challenging. Not sure I really know why. Well, yeah, it's probably not a very easy signal to. This is what you get, essentially. So estimate the number of change points from this. Where I would say none of the procedures is doing really well, but we're doing the least badly here. So 32, 33. Segmenter 3's back is beginning to do badly here. So it's not really there in the competition anymore. And then teeth, again, we're doing pretty well, but none of the other competitors come close. And stairs is interesting because stairs is the only signal where my wideband segmentation with the Schwarz information criterion is not in bold. But it's not a disaster. It's mostly overestimates by 1. It's not an easy signal to work with, because this is what you get. So it's not even, how many change points are there? Are there any is this a change point model? Yeah. So that's interesting. So yeah, it's not a disaster here, but there are better methods for that particular signal. And again, so segmented, and for some reason, some signals, this completely falls apart, this method. I don't know why. Again, I use it with a default parameter value, so I didn't do any optimization. I didn't even attempt any optimization. Okay, I don't have time, so I will just mention that for the data set I showed at the beginning, this shows the same data set, but in the price domain, in the variance stabilized price domain, where my change points are reflected by the vertical lines. So I should just say that this, of course, here, so this is, don't forget what it is, it's S&P 500 with the volatility removed. So this thing here, of course, the recent financial crisis, this dip here, and then it goes back. So the parameter value, so this is the most conservative change point estimate, and then the thin vertical lines are the least conservative, are the less conservative change points, and the broken lines are the least conservative change points. So we can see that this big dip where we have the start and the end of the financial crisis only gets detected for the slightly less conservative thresholds. So that means, but of course, probably most people on the street would agree that there have been some change points in the at the start and at the end of the financial crisis. So why don't we detect them? Well, we don't detect them because we've removed the volatility. So this really shows, this is yet another way of arguing for the leverage effect, that without volatility, those changes are perhaps not so significant. If you add volatility onto that, then they do become very significant. I should have shown them, but then those change points get detected to start with, not only later. But again, I'm running out of time. This is probably more interesting. So if we think a little bit about this procedure and about the problem, then we may or may not agree that that's at least that's my point of view, that change point detection is neither a completely local procedure, because sometimes we have one change point which is only visible globally, and it's not entirely global either, because sometimes we have those localized change points. So it's a mix between a local and global problem, which may mean that some sort of multi-scale approaches, which this one is, because it looks at long intervals and short intervals, might be useful. So that's certainly what this is trying to do. It's trying to offer some sort of multi-scale approach, which is, of course, agrees with the previous speakers' thoughts as well. Now, even more interestingly, I wonder if we can have similar local, global, randomized approaches in other non-parametric problems. You know, why fit functions with steps? Why not fit local linear functions, etc., and randomize the whole thing and combine in the same way? And speaking of randomized approaches, of course, recently it's a very hot thing in statistics, randomized approaches as a way of dealing with, as a way of trying to solve computationally complex problems. For example, there were some talks in last summer in the JSM, or I can't remember where people were trying to do a PCA of enormous matrices. And then how do you do that? Well, you can have a randomized approximate solution, which does exactly that. So it provides an approximate solution, but provides a fast solution. And that's I think that's in the same sort of strand of thinking, that you have a solution which is in some sense approximate, but it's quick because of the randomization. It's not exactly that, but it's the same idea essentially. All right. So okay. So the paper is under revision, and the latest versions on my website. And now there's a package, wild binary segmentation package, which was very expertly coded mostly by my student Rafał. And it's on CRAN. I don't have Rafał's photo, but I'm sure you will meet him. Most of you will meet him soon. Thank you very much.
So I was wondering how important the binary segmentation part of the WBS is. In other words, if you just have your intervals, you rank them by their best concern, and you just...
It's, as I was trying to say, it's very, very important. It's a very good question as well. And that's because think of, we need some hierarchization. And that's because if we have a Q-sum here, which corresponds to the one we want to choose, and now we have another Q-sum here, which corresponds to the same change point. Yeah, I can't include them both, because then they will both be estimating the same change point, and I will have a double estimate. Yeah, so I need to remove one of them. Which one to remove? Of course, the smaller one. Now, to remove the smaller one, that already implies some hierarchy. I need to sort them before I do any removal, and it's that sorting that corresponds to the binary stage, if you like. That's a way of doing my binary segmentation. I don't really do binary segmentation, but I do something like it, because I need to remove those spurious change, those probably spurious change. It's a very good question.
If I understood at the beginning, you assume for your procedure that the error terms are IID normally distributed. I think that the normally distributed can be somehow relaxed with the independence also, but you can use, in fact, there is a kind of these QSUM procedures. What you probably had in mind is, for me, based on the least squares.
Yes.
Yeah, but I think that everything can be, yeah.
Right, of course. So you're absolutely right. Everything. So the distribution of the errors can be relaxed, and in fact, my student is working on that. And yes, of course. So here I'm using least squares. I can use another fit if I like, and this least squares happens to be equivalent to this QSUM, which this is a QSUM.
Yeah.
Yeah. So I mean, I can do so, but I think I like to think kind of beyond this. What really matters here is the generic idea of the procedure.
Yeah, that's clear. This is general, but I think that the same can be done parallelly with a small modifications for.
I agree. I absolutely agree. Yes. Thank you. Yes. That's true.
Just about the number of segments you need to sample. So do you have some? So you mentioned some numbers. But do you have some kind of approximation in terms of the relation between that and the number of observation, total observation? Did you try to take for small number of observation the optimal, like to cover all the space or something like that? Do you have some kind of ratio to tell that m after some m you get reasonable results? Jen?
Yeah, I think there are two things here. So one thing is you want to also minimize the randomness in the output, which is very, very small in this procedure, but it's there because it's a random procedure. You can, of course, have a non-random version of this. You can have a fixed design, and you can choose your intervals deterministically. There's nothing wrong with doing that. I mean, there are reasons why we might prefer random, but I won't go into that maybe. Well, for the choice of m, I would say that my experience so far tells me that the more the better, essentially. It's very simple. It's as simple as it.
I assume that the more the better.
Yeah.
I mean, do you have some, from your experiences, some m that in terms of the total length of the data that is consistent? So.
Yes. So this was one of the.
So you mentioned some.
So beyond this, unfortunately, I don't have beyond this and the practical advice that the larger the better. I don't have any more insight, unfortunately. Yeah. Also, another interesting question, if I can ask a question to myself, is how to draw those intervals.
Yeah.
I mean, yeah.
Well, unless there's any other burning questions, we'll postpone the rest of the discussion for coffee time.
Thank you very much. Thank you.